Chapter number 2, Chemical Families. We have seen that chemical elements are arranged into groups and periods on the periodic table, and that members of a particular group show similarities or consistency in their physical and chemical behavior. Elements in a group are said to belong to a chemical family. In this chapter, we shall look at selected chemical families and analyze their trends in behavior and properties. Group 1 elements. The elements in Group 1 except hydrogen are called alkali metals. They include lithium, sodium, potassium, and others. The atoms of alkali metals have one electron in their outermost energy level. Group 1 elements are very reactive metals. Lithium, sodium, and potassium are at the top. These metals are so reactive, they have to be stored under oil and have to be handled with care. Lithium is so soft, it can be cut with a knife. It has a shiny metallic luster when freshly cut, but left exposed to air, it quickly begins to tarnish due to reaction with air. This is sodium. It is even easier to cut, and again the soon tarnishes. Potassium is even softer and reacts quickly and tarnishes. Graduation in atomic sizes. Atomic radius is the distance from the center of the atom to the outermost energy level occupied by an electron or electrons. In alkali metals, the atomic radii increase down the group. This is because as you go down the group, there is an additional energy level on each subsequent atom. Group 1 elements have a single electron in their outermost energy shells. That being so, they form ions by losing that outermost electrons. When the electron is lost, the energy level is lost as well, since we cannot have an empty energy level. So the ionic radius is smaller than the atomic radius. Also, all electrons are attracted to the nucleus at the same time that they repel one another. The shown electron, one of the outermost electrons, is shielded from the nuclear attraction by the inner shells. At the same time, it also shields the other electrons from the nucleus. When this electron is lost, the partial shielding it provided to the other electrons is lost. As a result, they experience a greater effective nuclear charge and the ion is smaller than the original atom. Ionization energy. Remember, the nucleus is positively charged and the electrons are negatively charged. So the electrons are attracted to the nucleus, and it is this electrostatic attraction that holds the electrons in place and prevents them from escaping. This is called the effective nuclear charge. In order to remove the outermost electron from an atom, we need to apply some energy to overcome this nuclear attraction. This energy is called the ionization energy. Ionization energy is the minimum amount of energy required to remove an electron from the outermost energy level. If an electron is further from the nucleus, it experiences weaker attraction and thus it's easily removed or lost from the atom. So the ionization energy decreases with increasing atomic radius. So for group 1 elements, ionization energy decreases down the group. Another factor that affects ionization energy is electron shielding. The outermost electron is shielded from the nuclear attraction by the other electrons in the inner end. So the more the number of shells, the greater the shielding, and hence the less the attraction, which ultimately means the outermost electron is easily lost. Electron shielding thus increases down the group, and this further explains the reducing ionization energy down the group. Chemical properties of group 1 elements. Reaction with water. Lithium floats on water. It reacts immediately, fizzing on the water surface, evidence that a gas is being produced. By putting a tiny piece in a test tube, we can test the gas with a burning splint. A pop sound means it's hydrogen. A universal indicator shows that at the end of the experiment, the solution is alkaline. Lithium reacts with water to form lithium hydroxide and hydrogen gas. Sodium reacts more vigorously, fizzing on the surface. The gas produced is hydrogen, and the solution is alkaline. Sodium reacts with water to form sodium hydroxide and hydrogen gas. Sodium is more reactive than lithium. It is below lithium on the periodic table. Potassium is below sodium. So how do you expect potassium to behave? Potassium is obviously more reactive than sodium and lithium. It reacts vigorously, generating a lot of heat, which ignites the hydrogen produced. A universal indicator turns blue. Potassium reacts with water to form potassium hydroxide and hydrogen gas. The element below potassium must be explosive in water. And so alkali metals react with water to form the corresponding hydroxides and hydrogen gas. Combustion. Sodium burns in oxygen with a yellow flame to form a yellowish-white solid called sodium oxide. On its part, potassium burns in oxygen with a lilac flame, forming a white solid of potassium oxide. Lithium will also burn in oxygen to form lithium oxide. And so in general, alkali metals react with oxygen to form the corresponding metal oxides. Reaction with chlorine. When a hot sodium metal is lowered into chlorine gas, it bursts into flame and white sodium chloride is formed. Lithium reacts less vigorously with chlorine, while potassium will react explosively. Alkali metals react with chlorine to form their corresponding metal chlorides. Reactions with dilute acids. Whereas reactions of alkali metals with water are vigorous, reactions with acids are explosive and must not be performed in a school lab. These videos are only for purposes of learning. All the same, alkali metals react with dilute acids to form salts and hydrogen gas. So in summary, alkali metals are group 1 elements of the periodic table. They have 1 electron in their outermost energy level. Their atomic radii increase down the group because of the additional energy level on each subsequent element. They form ions by losing the outermost electron, which makes the ionic radii smaller than the atomic radii. Ionization energy decreases down the group because a larger atomic radius means weaker attraction of the outermost electron and ease of removal. Because of this, reactivity of alkali metals increase down the group. Softness increase down the group because larger atoms form weaker attractions in the metallic structure. For the same reason, boiling points decrease down the group. Next, alkaline earth metals. Alkaline earth metals are elements in group 2 of the periodic table. They are beryllium, magnesium, calcium, strontium, barium, and radium. These metals all have 2 electrons in their valence shell and can lose these electrons to form ions. This loss of electrons and the ultimate loss of the valence energy shell means that their atomic radii are larger than the ionic radii. Similar properties and behavior are also observed. Moving down the group, their densities and reactivity increases. Melting and boiling points decrease and the metals become softer. Just like their alkali metal neighbors, alkaline earth metals have metallic structures, and because of the free delocalized electrons, they are good conductors of electricity. But because the alkaline earth metal atoms each contribute 2 electrons to the delocalized region, they are better conductors than the alkali metals whose atoms contribute 1 electron each. The metallic structure also explains why they have very high melting points. The atomic radius increased down the group due to additional energy level. Ionization energy. We have said that ionization energy is the energy required to remove an electron from the valence shell. Notice that alkaline earth metals lose 2 electrons. The 2 electrons are however lost in succession and not simultaneously. That is to say, the atoms lose 1 electron at a time. That means we have 2 ionization energies. The first ionization energy, I1, is the energy required to remove an electron from a neutral atom. Considerably more energy is required to remove the second electron from the positive ion. This is called the second ionization energy, I2. As each electron is removed by ionization, the remaining electrons experience less electron-electron repulsion and greater effective nuclear charge because the number of protons exceed that of electrons. Thus, each subsequent ionization requires more energy. As in alkali metals, this ionization energy decreases down the group because of increasing atomic radii. Properties of alkaline earth metals. Unlike the alkali metals, which are soft and easy to cut, alkaline earth metals are hard and tough. Equally, they are less reactive compared to the corresponding alkali metals because whereas alkali metals lose a single electron, alkaline earth metals must lose 2 electrons to react. Reaction with water. Calcium reacts with water, producing a stream of bubbles indicating a gas is being liberated. This gas is hydrogen and calcium hydroxide is formed. Magnesium does not react with cold water. It will, however, react with steam to form hydrogen, which is ignited at the end. Magnesium oxide is also formed. Combustion. Magnesium burns in air with a brilliant blinding flame to form magnesium oxide. Calcium burns with a reddish-brown flame to form calcium oxide. And so alkaline earth metals react in air to form metal oxides. Reactions with dilute acids. When mixed with a dilute acid, magnesium reacts vigorously, liberating hydrogen gas, and a salt is formed. On its part, calcium reacts more vigorously with dilute acids than magnesium. And so alkaline earth metals react with dilute acid to form salts and hydrogen. Halogens. Halogens are elements in group 7. They are fluorine, chlorine, bromine, iodine, and astatine. Their atoms have 7 electrons in their valence shell and can accept 1 electron to form an ion. Halogens exist as diatomic molecules. The forces of attraction or intermolecular forces increase with increase in the size of the molecule. Moving down the group, atomic radii increase by 1 electron shell. As a consequence, melting point, boiling points as well as their densities increase. Chlorine and fluorine are gases. Bromine is a liquid and iodine and astatine are solids. Fluorine is a pale green gas. Chlorine is a greenish yellow gas. Bromine is a reddish brown liquid. Iodine is a gray solid that sublimes to a purple vapor. Astatine is a black solid and radioactive. Electron affinity. Halogens form ions by gaining an extra electron to complete an octet electron configuration. Electron affinity is the energy change that occurs when an electron is added to an atom or an ion. For example, when an electron is added to a neutral chlorine atom, 349 kilojoules are released. Electron affinity is the opposite of ionization energy. Generally, electron affinity increases as the atomic size increases, and hence the reactivity of halogens decreases down the group. Atomic and ionic size. When an electron is added to a neutral atom, it experiences a partial nuclear charge because it is shielded from the nuclear by the other electrons. It also contributes to shielding of the other electrons. The added electron also gives rise to increased electron-electron repulsion, and thus the resulting ion is larger than the original atom. Reactions of halogens. Fluorine is dangerous to handle, but we can compare the reactivity of the other halogens. This is iron wool. For it to react with iodine, it is placed above a few crystals in a boiling tube in a fume cupboard. Heating the iodine turns it into vapor. A Bunsen flame gets the reaction going. After several minutes of strong heating, only a small amount of iron has reacted. It has become coated with reddish-brown iron iodide. Put bromine in the place of iodine and it immediately vaporizes. Again, the iron wool needs heating, but not as much. This time, there is an easily visible reaction. A mixture of unreacted bromine and brown iron bromide pours out of the tube. Bromine is more reactive than iodine. It is above iodine in the periodic table. Chlorine is above bromine, so it should be more reactive. The apparatus on the left generate a stream of chlorine gas. Concentrated hydrochloric acid is slowly dripped onto potassium permanganate. This time, the iron wool needs the slightest nick of a flame before a violent reaction races along. Clouds of pale yellow iron chloride quickly form. Chlorine is very reactive, but fluorine is the most reactive halogen. Halogens also react with aluminium. Chlorine reacts violently with aluminium foil. It is not long before clouds of aluminium chloride leaves the tube. Bromine also have a brisk reaction with aluminium foil. Iodine and aluminium powder react once a drop of water has been added. and so halogens react with metals to form metal halides. The reactivity of halogens decreases down the group because the ability of an atom to gain an electron decreases as the atomic size increases. Reaction of chlorine with water. When a wet blue litmus paper is inserted in a chlorine gas jar, it turns red and then it's bleached. The bleaching action is due to a chlorine compound called chloric 1 acid. Chlorine dissolves in water to form chlorine water, which is a mixture of chloric 1 acid and hydrochloric acid. Chloric 1 acid oxidizes the dye in the litmus paper to a colorless compound and itself is reduced to hydrochloric acid. The bleaching would not occur on dry litmus paper because no chloric 1 acid will be formed. Left standing in sunlight, chloric 1 acid decomposes into hydrochloric acid and oxygen. Uses of halogens. In their elemental forms, halogens are toxic. However, their compounds are used in everyday life. Toothpaste usually contains sodium fluoride, which acts to prevent tooth decay. For the same reason, some countries fluorinate their water supply. We know of the non-stick pans. The reason why the pan is non-stick is due to a layer of Teflon, a fluorine-containing compound. Ever smelled a swimming pool? That smell is in fact due to a chlorine-containing compound, sodium hypochlorite. Now cleaning the bathroom and toilet sinks. Bleach is a common household cleaner and is also a compound of sodium hypochlorite. In both cases, sodium hypochlorite acts as a disinfectant. In other words, it kills germs. Many countries chlorinate their water supply as a safety measure. Common table salt is sodium chloride. It is a favoring agent and enhances food taste. In cold countries, people often salt the pavement of the driveway. Road salt is a mixture of sodium chloride and calcium chloride. The sodium and calcium chloride solution that results when ice starts to fall has a lower freezing point than that of water, so ice is not formed even at low temperatures. PVC or polyvinyl chloride is a certain type of plastic. It is used to make pipes, insulate electrical wirings, make waterproof clothing items, and important healthcare equipment. Aqueous solution of bromine can be used to test for alkenes or unsaturated hydrocarbons. It goes from orange to colorless in the presence of alkenes. In photography, the paper is coated with silver bromide, which darkens upon exposure to sunlight. Iodine can be dissolved in water or alcohol to be used as an antiseptic. Like disinfectants, an antiseptic also kills germs but is mild enough to be used on the skin. Iodine is needed in the diet and comes from seafood or iodized salt. Iodine deficiency leads to enlarged thyroid gland, a condition called goiter. Last family, the noble gases. The noble gases are the group 8 elements: helium, neon, argon, krypton, xenon, and radon. These elements are notable for having a full valence shell of electrons. Helium has 2 valence electrons, whereas the others each has 8 electrons. This makes them very stable elements. In fact, they are so stable that in the past, chemists thought that they could not react with other elements, which is why they were called inert or unreactive gases. However, today we know that some noble gases can indeed react to form some compounds, which is why today this group of elements is called the noble gases instead. Noble gases are colorless and monoatomic, meaning they exist as single atoms. Moving down the group, the number of energy levels increased by 1, and hence the atomic radii increase down the group. The size of the atom also affects its boiling point. The boiling points increase because intermolecular forces between larger atoms are greater than that between smaller atoms. Also moving down, the densities of the gases increase because larger atoms take up more space in a set volume. Because they are very stable and hardly react, as well as their individual characteristics, noble gases have many practical real-life applications. One you might already know is helium, used to fill balloons. Since it is less dense than air, these balloons float. Because of this property, it is also used to fill airships. Krypton and xenon are used in some types of lasers, and xenon is used in car headlights to increase visibility. Xenon lamps produce very bright light and increase contrast and color vision. Although it is inert, when an electric current is passed through neon, it emits a bright orange light. Light bulbs are filled with argon. Unlike air, it won't react with the tungsten filament. Now we look at properties and trends across a period. As we have discussed earlier, elements in the same period have the same number of occupied energy levels. As you move across the period, the number of electrons in the outermost energy level increases by 1. While the elements in the same group exhibit similar properties, those across a period show gradual change in properties. And this we can illustrate by considering elements in period 3 from left to right. The elements in period 3 are sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Electrical conductivity. Sodium, magnesium, and aluminium have delocalized electrons in their structures. These delocalized electrons are responsible for the conduction of electricity. Conductivity increases with increase in the number of delocalized electrons, and therefore, aluminium with 3 delocalized electrons from each atom in the structure has the highest electrical conductivity. Phosphorus, sulfur, chlorine, and argon are all made up of molecules and therefore are non-conductors of electricity. Silicon is unique among the elements because it is a semiconductor. Its electrical conductivity increases with increase in temperature. The atomic radii of the elements gradually decrease across the period from left to right. This is explained by the increase in the nuclear charge across the period due to an increase in the number of protons. Although there is an additional number of electrons, they enter the same energy level. This means that the shielding effect remains the same as nuclear charge increases. The forces of attraction between the nuclei of these elements and the electrons in the outermost energy levels progressively increase across the period. As a result, the electrons in the outermost energy level are pulled closer to the nucleus, thereby decreasing the size of the atoms across the period from sodium to argon. Sodium, magnesium, and aluminium have giant metallic structures. They have strong metallic bonds. These bonds require a lot of energy to break, and hence the high melting and boiling points. Aluminium contributes 3 electrons to the metallic lattice, whereas sodium contributes only 1. Also, due to the small size of the aluminium atom, the packaging of the atom is closed, and therefore the metallic bonds in aluminium are stronger than in sodium and magnesium, and hence the higher melting point and boiling points of aluminium. Silicon has a giant atomic structure in which all the atoms are held together by strong covalent bonds. This needs a lot of heat energy to break, and hence the high melting and boiling points of silicon. In contrast, phosphorus, chlorine, and argon are molecular. The atoms in the molecules are held together by strong covalent bonds, while the molecules themselves are held together by van der Waals forces, which require little energy to break. Melting involves breaking the van der Waals forces.